Hello and welcome to the Machine Learning Podcast, the podcast about going from idea to delivery with machine learning. Building good ML models is hard, but testing them properly is even harder. At DeepChecks, they built an open source testing framework that follows best practices, ensuring that your models behave as expected. Get started quickly using their built-in library of checks for testing and validating your model's behavior and performance, and extend it to meet your specific needs as your model evolves. Accelerate your machine learning projects by building trust in your models and automating the testing that you used to do manually. Go to themachinelearningpodcast.com/deepchecks today to learn more and get started. Your host is Tobias Macey, and today I'm interviewing Max Halford about River, a Python toolkit for streaming and online machine learning. So Max, can you start by introducing yourself?
Oh, hey there. So I'm Max. Yes, I consider myself as a data scientist. My day job is doing data science. I actually measure the carbon footprint of clothing items. But I have a wide interest in technical topics, be it software engineering or data engineering. Do a lot of open source. My academic background is leaning towards finance and computer science and statistics. I actually did a PhD in applied machine learning, which I finished a couple of years ago. So yeah, an all-around nerd, basically.
And do you remember how you first got started working in machine learning?
Kind of, yes. I was a late bloomer. I got started when I was 21, 22, when I was at university. I basically had no idea what machining was, but I started this curriculum that was around statistics. And we had a course, which was maybe 2 or 3 hours a week about machine learning. And it did kind of blow my mind. It was around a time when, machine learning and particularly deep learning was starting to explode. So I kind of started at university. So I was lucky enough to get a theoretical training.
And in terms of the River project, can you describe a bit more about what it is that you've built and some of the story behind how it came to be and why you decided that you wanted to build it in the first place?
When I was at university, I received a kind of regular introduction to machine learning. Then I did some internships. I started a PhD after my internships. And I also did a lot of carol competitions on the side. So I was kind of hooked into machine learning. And it always felt to me that something was off, because when we were learning machine learning, everything made sense. But then when you get to do it in practice, you often find that, it's not playgrounds. Like the playground scenarios that they describe at university or when you learn machine learning just do not apply in the real world. The real world, you have data that's coming in, like a flow of data, or every day there's new data, or there's like an interactive aspect to the world around us, the way the data is flowing. It's not like a CSV file. Yeah, it just felt like fitting a square peg in a round hole. So I was always curious in the back of my mind about how you could do online machine learning. Well, I didn't know it was called online machine learning, because when I was a kid, I remember growing up and thinking that AI was this kind of intelligent machine that would keep learning as it went on and as it experienced the world around it. Anyway, when I started my PhD, I was lucky enough to have a lot of time to read. So I read a lot of papers and blog posts and whatnot. And I can't remember the exact day or week that I stumbled upon it, but I just started learning about online machine learning, maybe some blog posts or something. And then it was like a big explosion in my head. And I was like, wow, this is crazy, right? This actually exists. And I was so curious as to why it wasn't more popular. And at the time, I did a lot of open source as a way to learn. And so it just felt natural to me to start implementing algorithms that I'd read in papers on everywhere. I just started writing code to learn, basically, just to confirm what I'd learned and whatnot. That's just the way I learn. And it kind of evolved into what it is, which is an open source package that people use. Now, if I may expand a little bit, River is actually the merger between two projects. So the first project is called Scikit Multiflow. It was a package that was developed before I even got into machine learning. It has roots in academia in New Zealand. It comes from an old package called Moa in Java. Anyway, I wasn't not aware of that. On my end, I started a package called Cream at the time. So in French, crème means a cream, and it played funny with incremental, which is another way to say online. So I developed Cream by myself. And at some point, it just made sense to reach out to the guys from Psyche Multiflow and to propose a merger. So it took us quite a while, but after 9 months of negotiation and figuring out the details, we merged and we called the new package River.
You mentioned that it's built around this idea of online machine learning, and in the documentation, you also refer to it as streaming machine learning. I'm curious if you can just talk through what that really means in the context of building a machine learning system and some of the practical differences between that and the typical batch-oriented workflow that most folks who are working in ML are going to be familiar with.
First, just a recap on machine learning. The whole point of machine learning is to teach a model to learn from data and to take decisions. So, monkey see, monkey do. And the typical way you do that is that you fit a model to a bunch of data, and that's it really. But online machine learning is the equivalent of that, but for streaming data. So you stop thinking about data as a file or a table in a database, but you think of it as a flow of data, a stream. So online machine learning, you could call it incremental machine learning, you could call it streaming machine learning. I mean, I more often see online machine learning being used, although if you Google that, you kind of find these online courses to learn online machine learning, so that's not kind of cool online. But anyway, yeah, it's just this way to say, can I do machine learning, but with streaming data? And so the rule is that an online model is one that can learn one sample at a time. So usually you show a model a whole data set and it can work with that data set. It can calculate the average of the data set, it can do a whole bunch of stuff. But the restriction here with online machine learning is that the model cannot see the whole data, it can't hold it in memory, it can only see one sample at a time. And it has to work like that. So it's a restriction, right? So it makes it harder for the model to learn, but it also has many, many implications. If you have a model that can learn that way, well, you can have a model that just can keep learning as you go on. Because a regular machine learning model, once it's been fitted to a dataset, you have to retrain it from scratch if you want to incorporate new samples into your model. That can be a source of frustration. And that's what I was calling the square peg in the round hole before. So say you have a model, an online model that is just as performant as a batch model. Well, if you just, regardless of performance, accuracy, that has many implications, and it actually makes things easier, because if you have a model that can keep learning, well, you don't have to, for instance, schedule retraining of your model. You can just, every time you have a new sample that arrives, you can just tell your model to learn from that, and then you're done. And so that ensures that your model is always as up to date as possible. And that has obviously many, many benefits. If you think about people working on the stock market, so trying to forecast the evolution of a particular stock, they've actually been doing online machine learning since the 80s, because obviously they have a lot to lose by making all this public. It just never got into a big thing, and it always stayed in stock market companies. So the practical differences are that you are working with a stream of data. You're not working with a static data set. This stream of data has an order, meaning that the fact that one sample arrives before the other, well, that has a lot of meaning, and that's actually reflecting what's happening in the real world. In the real world, well, you have data that's arriving in a certain order. Well, if you train your model offline on that data, you want to, process it in the same order. And so that ensures that you are actually reproducing the conditions that happen in the real world. Now, another practical consideration is that online learning is much less popular or predominant than batch learning. And so a lot less research and software work has been put into online learning. So if you are a newcomer to the field, well, there's just not a lot of resources to learn from. Actually, you could just spend a day on Google and you probably find all the resources there are, because there's just not so many of them. There's probably, like, by memory, just 10 links on Google that you can learn from about online learning. So it's a bit of a niche topic.
In terms of the fact that batch is such a predominant mode of building these ML systems, despite the fact that it's not very reflective of the way that the real world actually operates, why do you think that's the case, that streaming or online machine learning is still such a niche topic and hasn't been more broadly adopted?
Sometimes it feels like I'm trying to preach a new religion. It always feels a bit weird because there's not a lot of us doing it. So I'm also I never try to force people into this. There's obviously many good reasons why batch learning is still done. Now, from a historical point of view, I think it's interesting because we always used to use statistical models to explain data and not necessarily to predict. So you just have a data set and you just like to understand, what variables are affecting a particular outcome. So for instance, if you take linear regression, historically it's been used to explain the impact of global warming on the rise of sea level, but not necessarily to predict if the temperature of the globe was higher, what would be the impact on the sea level. But then someone said, let's use machine learning to predict outcomes in a business context. And that's why we have this big advent of machine learning. And we've kind of been using the tools that have been lying around. So we've been using all these tools that were used for to a data set and explain it, but now we've been using them for predicting. So these models are static. Like the people who, when we started doing linear regression, we never really worried about streaming data because data sets were small, data sets were static. Well, the internet didn't even exist. So there was no real notion of IoT or sensors or streaming data. So the fact is that we've never needed online models. And so as a field, if you look at the academia and the industry, we're very used to batch learning and we're very comfortable with it. There's a lot of good software and this is what people are being taught at university. So I'm not saying that online learning is necessarily better than batch learning, but I do think that the reasons why batch learning is so predominant in comparison is because we are too used to it, basically. And I do think that, and I see it every week, people who are trying to rethink their job or their projects and saying, maybe I could be doing online learning. It actually makes more sense. So I think it's a question of habits, really.
For people who are assessing which approach to take in their ML projects, what are some of the use cases where online or streaming ML is the more logical approach, or what the decision factors look like for somebody deciding, do I go with a batch-oriented process where I'm going to have this large set of tooling available to me, or do I want to use online or streaming ML because the benefits outweigh the potential costs of plugging into this ecosystem of tooling?
So I'll be honest, I think it always makes sense to start with a batch model. Why? Because, if you're pragmatic and you actually have deadlines to meet and you just want to be productive, there's so many good solutions to train a batch model and deploy it. So, I would just go with that to start with. And then, there's the question of, could I be doing this online? So I think there's two cases. There's cases where you need it. And so I have a great example. So Netflix, when they do recommendations, you arrive on the website and Netflix recommends movies to you. Netflix actually retrains a model every night or every week, but they have many models anyway, but they are learning from your behavior to kind of retrain their models to update their recommendations, right? There's a team at Netflix that are working on learning instantly. So if you are scrolling on the Netflix website and you see a recommendation from Netflix, the fact that you did not click on that recommendation is a signal that you do not want to watch that movie, maybe, or that the recommendation should be changed. So if you're able to have a model, for instance, maybe in your browser, that would learn in real time from your browsing activity, and that could update and learn on the fly, that'd be really powerful. And the only way to do that is to have a model per user that is learning online. And so you cannot just use batch models for that. You can't just, every time a user scrolls or ignores a movie, you can't just take all the history of data and fit the model. It would be much too heavy and it's just not practical. So sometimes the only way forward is to do online learning. But again, this is quite niche, like Netflix recommendations. I mean, obviously are working reasonably well, I believe, because they're, just from their market value. But if you are pushing the envelope, then sometimes you need online learning. Now, another case is when you do not necessarily need it, but you want it because it makes things easier. So a good example I have is, imagine you're working on an app that categorizes tickets. So for instance, on the help support software. So, you go on a website and you're filling a form, or you send a message or an email and you're asking, you have some problem maybe with a reimbursement on something you bought on Amazon. And then, there's a customer service behind that, human beings that are actually answering those questions. And it's really important to be able to categorize each request and put it into a bucket so that it gets assigned to the right person. And maybe the product manager has decided that we need a new category. And so there's this new category, and your model is classifying tickets into one of several categories. If you introduce a new category, it means that you have to retrain the model to incorporate it. I was in discussion with a company, and they were only able to, or their budget was that they were only able to retrain the model every 3 months. So if you introduced a new ticket, a new category into your system, the model would only pick it up and predict it after 3 months. So that sounded kind of insane and wasn't predictive at all. And I was not aware of the exact details, but it just seemed too expensive for them to retrain their model from scratch. So if they were using an online model, well, potentially that model could just learn the new ticket on the fly. And, if you just introduced it and people started, you'd imagine this feedback loop where you introduce a new category, people send the email, maybe a human assigns that ticket to a category. So that becomes a signal for the model picks that up, learns, and it's going to incorporate that category into its next predictions. So that's a scenario where you don't necessarily need online learning, but actually online learning just makes more sense and makes your system easier to maintain, to work with, basically. Yeah.
There are a number of interesting things to dig into there. One of the things that you mentioned is the idea of having a model per user in the Netflix example. And I'm wondering if you could maybe talk through some of the conceptual elements of saying, okay, I've got this baseline structure for this is how I'm going to build the model. Here is the initial training set. I've got this model deployed, and now every time a specific user interacts with this model, it is going to learn their specific behaviors and be tuned to the data that they are generating. Would you then take that information and feed that back into the baseline model that gets loaded at the time that the browser interacts with the website? And just some of the ways to think about the potential approaches for how to say, okay, I've got a model, but it's going to be customized per user, and just managing the kind of fan out, fan in topologies that might result from those event-based interactions spread out across n number of users or entities.
Now, it sounds insane when you say it, because to have one model per user and have it deployed on a user's browser or mobile phone or God knows what, on Apple Watch, it does kind of sound insane, but it is interesting, I guess. I don't think there are so many. I mean, I'm not aware of a lot of companies that would have the justification to actually do this, and I've never had the occasion to actually work in such a setting where I would do this. But I had one good example where I was kind of doing some pro bono consulting. It was this car company where the onboard navigation system, they wanted to build a model where they could guess where you're going to. So basically, depending on where you left, if you left home in the morning, you're probably going to work. And they would then use this to, just send you news about your itinerary or things like that. They really needed a model that would just be able to learn online. And they made the bold decision to say, okay, we're going to embed the model into the car. It's not going to be like a central model that's, hosted on some big server and that the car interacts with. Actually, the intelligence is actually happening in the car. And so when you think about that, it's really interesting because it creates a decentralized system. There's not like a single, it actually creates a system where you don't even need the internet for the model to work. So there's so many operational requirements for that. Actually, now that I think of it and I'm talking about cars, I realize that that's actually what Tesla is doing, right? They're computing and making decisions inside the car, doing a bunch of stuff, and they're also communicating with mother servers, but the actual computer, they actually have GPUs in the car doing compute with their deep learning models and whatnot. So it's definitely possible to do this, right? But clearly not something that a lot of companies would go through or would have the need to do.
It's interesting also to think about how something like that would play into the federated learning approach, where you have federated models where there is that core model that's being built and maintained at the core. And then as users interact at the edge, whether it's on their device or in their browser, it loads the federated learning component that has that streaming ML capability. So the model evolves as the user is interacting with it on their device, and then that information is then sent back to the centralized system to be able to feed back into the core model, so that you can have these kind of parallel streams of the model that the user is interacting with is being customized to their behavior at the time that they're interacting with it, but it does still get propagated back into the larger system so that the new intelligence is able to generate an updated experience for everybody who then goes and interacts with it in the future.
Yeah, that's really, really interesting. So I think first off, the fact is that I'm actually still young and there's so many things that I don't know, and I don't have like the technical savvy to be able to suggest ways forward. But this is obviously things that, I think about. So there's things like Hogwild, which is a project from Google. They have a paper where they discuss these things. I think that's a really simple thing that if you wanted to do this, if you're the listener wanting to do something like this, I think there's a simple pattern, which is to maybe once a month have a model that is retrained and that you just train in batch. And that model is going to be, it's going to be like a Hydra. Like you're going to copy it and you're going to send it to each user. And then each copy for each user is going to be able to learn in its own environment. And for instance, a good idea would maybe your model to increase like the learning rate so that every sample that the user gives you matters a lot. So for instance, if we take the Netflix example, you would have, your run-of-the-mill recommendation system model that you would just train in batch, and you just use all the tools that we in community use. But then you would embed that into each person's browser, and maybe you do this once a month. And then that model for each user would be a copy, a clone, or like just a separate model now. And, it would keep learning in an online manner. So maybe your model was trained in batch initially, but now for each user, it's actually is being trained online. And so, for instance, you can do this with factorization machines that can be trained in batch, but also online. And yeah, you would use a high learning rate so that every sample matters a lot, basically. And so you, the user, are tuning your model. And so I don't know how YouTube does it, for instance, but I do imagine they have some sort of core model. They're just learning how to make good recommendations. But obviously, YouTube, there are some rules that make it so that, recommendations are tailored to each user. And I don't know if this is done online, and I don't know if it's actually machine learning. It's probably just rules or scores. But yeah, I think it's a really fun idea to play around with. And I do think that online learning enables this even more.
As far as the operational model for people who are using online and streaming machine learning, if they're coming from a batch background, they're going to be used to dealing with the train, test, deploy cycle where I have my data set, I build this model, I validate the model against the test data set that I've held out from the training data. Everything looks good based on the area under curve or whatever metrics I'm using to validate that model. Now I'm going to put it into my production environment where maybe it's being served as a Flask app or a Fast API app. And then I'm going to monitor it for concept drift. And eventually I say, okay, this is no longer performing up to these specifications. So now I need to go back and retrain the model based on my updated data sets. And I'm wondering what that process looks like for somebody building a streaming ML model with something like River, and how you address things like concept drift and how concept drift manifests in this streaming environment where you are continually learning and you don't have to worry about the real world data that I'm seeing is widely divergent from the data that I use to train against.
There's so many things to dig into, and I'll try to give a comprehensive answer. So first off, it's important to understand that River itself is to online learning what scikit-learn is to batch learning. So it only desires to be a machine learning library, right? So it just contains basically algorithms, routines to train a model and to have models that can learn and predict. And what you're going towards to with your question is ML ops. So how does a life cycle look like for an online model? And so this is obviously something that I'm spending a lot of time to look into. The answer is that the first part of the answer is that online learning enables different patterns. And I believe that these patterns are simpler to reason about. So, as you said, you usually start off by training a model, then evaluating it against a test set, and maybe going to report to your stakeholders and show them the performance and guarantee that, the percentages of false positives is underneath a certain threshold, and yes, we can diagnose cancer with this model or not. And yeah, and then you kind of deploy it, maybe if you get lucky, if you get the approval, and you sleep, well or not well at night, depending on how much you trust your model. But there's this notion of you deploy a model and it's like a baby in the world, and this baby is not going to keep learning. So, it's a lie to believe that if you deploy a batch model, you're going to be able to just let it run by itself. There's actually maintenance that has to happen there. So the reality is that any machine learning project, any serious project, is never finished. It's like software, basically. We have to think of machine learning projects have software engineering, and obviously, we all know that you never just deploy a feature, a software engineering feature, and just never look at it. You monitor it, you take care that, investigating bugs and whatnot. So batch learning in that sense is it's a bit difficult to work with, because obviously you can have, if your model is drifting, so meaning that its performance is dropping because the data that it's looking at is different than the training set it was trained on, you basically have to be very lucky if you want your model to pick up performance. So you're going to have to do something about it. And yeah, you can just retrain it. But what you do with online learning is that you can have the model just keep learning as you go. So there is no distinction between training and testing. What online learning encourages you to do is to deploy your model as soon as possible. So say you have a model and it's not been trained on anything, well, you can put it into production straight away. When samples arrive, it's going to make a prediction. So maybe, user arrives on your website, you make recommendations, that's your prediction. And then your user is going to click or not on something you recommended to her. And that's going to be feedback for your model to keep training. So that is already a guarantee that your model is kind of up to date and kind of learning. And so that's really interesting, because just enables so many good patterns. You can still monitor the performance of your model. If the performance of your online model is dropping, I mean, I haven't seen that yet, but it probably means that your problem is really hard to solve. So a really cool thing I stumbled upon was this idea of test then train. So the idea that, imagine this scenario where you have a classification model that is running online. And so what would happen is that you have your model is generating features. So say the user arrives on the website and the features are, what's the time of the day, what's the weather like, what are the top films at the moment. And these are features. And these are features that you have at a certain point in time t. You generate these features, and then later on, when you get the feedback, so did your recommendation, was it a success or not? That's training data for your model. You use the same features that you used for predictions. You use those features for training. And so you can see here that there's a clear feedback loop. The event happens, the user comes on the website, your model generates features, and then at some later point in time, the feedback arrives. So was the prediction successful or not? Or if so, if not, by how much was the error? And then, you can use this feedback, join it with the features that you generate for predicting, and use that as training data. So, and you essentially have like a small queue or a database that's storing your predictions, your features, and your training data, and the labels that make your training data. So the big difference here is that you do not necessarily have to do a training test phase before deploying your model. You can actually just deploy your model initially and it just learns online, and then you can monitor. A really cool thing is that If you do this, you have a log of people coming on your website, you making predictions, you gain features, people clicking around and interacting with your recommendations. This creates a log of what's happening on your website. And so this log, what's really cool is that you can offline afterwards, after the fact, you can process it in the same order it arrives in, and you can replay the history of what happened. So it means that if you, on the side, when you're redeveloping a model or you want to develop a better model, you can just take this log of events, run through it, and do this prediction and training dance, the whole life cycle. You replay the feedback loop, and then you have a very accurate representation of how your model would have performed on that sequence of events. So that's really powerful, because the way you're designing your model there is that you have a rough sketch of a model which you deployed, and then you have a log of that model. So you can evaluate the performance of that model, but more importantly, you can have a log of the events. And then when you're designing the version 2 of your model, you have a very reliable way to estimate how your new model would have performed. And that's really cool, because when you're doing train test splits in batch learning, that is not representative of the real world. The whole problem is that what you're doing with train and test is people are spending so much time making sure that their train test split is correct, when in fact, even having a good train and test split is not a good proxy of the real world. A good proxy of the real world is to just replay through history. So, and that's something that you can only do with online learning. So that's really cool. Now, to come to your point about concept drift. So concept drift, there's many different kinds of concept drift, and Chip Hewen has a really good article on that on her blog. What matters really is that concept drift, the result of it is usually that your model is not performing as well, right? It's going to be a drop in performance. And so the first thing you see in your monitoring dashboard is that a metric has dropped. And then when you dig into it, you see that maybe there's a class imbalance, or that the correlation between a feature and a class has changed, or something like that. So essentially saying that the data the model has been trained on is not representative of the new data that is being seen in production. But again, I've already said this a few times, but online models, if you put them in place with a correct MLOps setup, they are able to learn as soon as possible. So that just guarantees that your model is as up to date as possible. So you're basically really doing the best you can. So drift is always possible. You can always obviously have a model that's degrading or that's just going haywire. That's not related necessarily to the online learning aspect of things. And so there are also ways to cope with this. So for instance, Dan Crankshaw and his team at Berkeley, they developed a system called Clipper. It's a kind of MLOps tool. It's a research project, but I think it's been deprecated, but the ideas are still there. It's a project where they have a meta model, which is kind of looking at many models being run in production and deciding online which model should be used for making prediction. So it's kind of like a teacher selecting the best student at a certain point in time, and kind of seeing throughout the year how the students are evolving and like which students are getting better or not good. And so you can do this with bandits, for instance. But yeah, so just to say that there are many ways to deal with concept drift, but online models again help to cope with concept drift in just a way. Actually, it just makes sense more so than batch models.
And so digging now into River itself, can you talk through how you've implemented that framework and some of the design considerations that went into how do I think about exposing this online learning capability in a way that is accessible and understandable to people who are used to building batch models?
So I like to think of River more as a library than a framework. If I'm not mistaken, a framework kind of forces you into a certain behavior or way to do things, and there's an inversion of control where the framework is kind of deciding things for you. So if you look at Keras and PyTorch, Keras is very much more a framework in comparison to PyTorch, because PyTorch, for me, the reason why it was successful is that it kind of gave inversion of control towards the user. You can do so many things in PyTorch, and it's very flexible and doesn't really impose a single way of doing things. So we have that in mind with River. River, again, is just a library to do machine learning, online machine learning, but it just contains the algorithms. It doesn't really force you to, read your data in a certain way, or you could use it in a web app, you could use it offline, you could use it on an offline IoT sensor. River is not concerned with that. It's just a library that is agnostic with regards to that. So now to come in to what River is, it is, in terms of online machining, it is general purpose. So it's not dedicated to anomaly detection or forecasting or classification. It covers all of that. That's the ambition, at least. So just a note there is that it's actually really hard to develop and maintain, because other maintainers and we are not necessarily specialized in different domains, and we kind of have to, one day I'm going to be working on the forecasting module of it, and the other day I'm going to work on anomaly detection, and it's kind of crazy. So it's still fun. What we do provide is a common interface. So just like scikit-learn, every piece of the puzzle in River follows a certain interface. So we have transformers, we have regressors, we have anomaly detectors, of course we have classifiers, so binary and multi-class. You have forecasting models for time series. And so we guarantee to the user that each model follows a certain API. So every model is going to be able to have a learn method, so it can just learn from new data. And they usually have a predict method to make a prediction. And so forecasters will have a forecast method. Anomaly detectors will have a score method, which outputs a anomaly score. And so the strength of River is to provide this consistent API for doing online machine learning. And it's a bit opinionated because it like scikit-learn, really. It just says, okay, you can have learn and predict, but that's a reasonable thing to impose. And that makes it easier for users to switch in new models because they have the same interface. And so again, just to conclude on what I said at the start, we made the explicit choice to follow the single responsibility principle, in that River only manages the machine learning aspect of things and not the deployment and whatnot. And so if you wanted to use River in production, see people doing this, you have to worry about some of the details yourself. Like if you want to deploy in a web app, well, we do not help at the moment at all with that. You have to deploy your own web app.
As far as the overall design of the framework, you mentioned that it actually started off as two separate projects, and then you went through the long process of merging them together. I'm wondering, how have the overall design and goals of the project changed or evolved since you first started working on this idea?
The reason actually why the merger between Cream and Scikit Multiflow took us a long time was that although we were both online learning libraries, there were some subtle differences which were kind of important. So my vision with Cream at the time and River now is that we should only cater to models which are what I call pure online models, in that they can learn from a single sample of data at a time. But there are also mini batch models, so models which can learn from streaming data but in chunks, so like in a mini batch of data. And Scikit Multiflow was kind of doing this, so much like PyTorch and TensorFlow and deep learning models. And so I kind of had to convince them that there were reasons why it was just a bit better. Why? Because, if you think about, again, a user interacting on a website or just any web requests or things that are happening in the real life, you want to learn as soon as possible. You don't want to have to wait for, 32 samples to arrive to have a batch to be able to feed that to your model. You could, obviously, but it just made sense to me to have something simpler where we only care about pure online learning, because it means that you don't have to store anything. You just learn on the fly. And so I guess the interaction I had with Scikit Multiflow kind of confirmed this idea. And I guess, they were a bit doubtful when we did the merger and maybe I was a bit too opinionated, but history proved that it actually made sense. And it's not a decision that we look back on. Like, we're really happy with this now. So River has, arguably moderate success. So it's working, it's alive, it's breathing. It's been going on for 2 years and a half, the project. And so we have a steady intake of users that are adopting it. And, we see this from emails we receive, from GitHub discussions and issues, and just general feedback we get. So the general idea of having a library that is only focused towards ML and just the algorithms is something that we are just going to keep going with, because it looks like it's working. It looks like this is what people want. A simple example is hey, I want to compute a covariance matrix online. Well, River aims to be the go-to library to answer those kind of questions, right? But the truth is that people, they don't just need that. They also need ways to deploy these models and do ML ops online. So, well, we basically, the next steps are for us to build new tools in that direction. Now, we also think that the initial development of Rivers was a bit fast and furious. The aim was to implement as many algorithms as possible and, just to cover the wide spectrum of machine learning. Now that we've, covered quite a few topics, and we also have day jobs. So when I was developing River initially, I was doing a PhD. So ironically, I had more time than now because I have a proper job, but we value our time a bit more, and we're not in this fast and furious mode. We kind of just focus on picking certain models which are valuable and we see value in, and just spending time to implement them properly. And we also see the final aspect is that we see that people, they don't just want, well, our user base does not just want algorithms, they also want us to educate them. So they have general questions as towards, what is online learning and how do I do it and how do I decide what model to use, and, all the questions that we're covering in this podcast, basically. So I think there's a huge need for us to kind of move into a educational aspect. So when I was younger, scikit-learn was my Bible. Like, I would just spend so much time not even using it, not even just using the code, but actually just reading through their documentation because it's just so excellent. So obviously that takes a lot of time, a lot of energy, and people, contributors and help, but definitely something towards which we're moving.
In terms of the overall process of building the model using something like River, when people are building a batch model, they end up getting a binary artifact out that is the entire state of that model after it has gone through that training process. And I'm curious if you can talk to how River manages the stateful aspect of that model as it goes through this continual learning process, both in a sandbox use case where somebody's just playing around on their laptop, but also as you push it into production where maybe you want to be able to use this model and scale out serving it across a fleet of different servers, and just some of the state management that goes into being able to continually learn as new information is presented to it.
So batch learning, the great advantage of batch learning is that once you train your model, it's essentially a pure function. There are no side effects. The decision process that's underlying the model is not going to change. So, you can push the envelope and compile it. You can pickle it. You can convert it to another format. So that's what ONNX does. You can compile it so that it can run on a mobile device. I mean, it does not need the ability to train anymore. It's just basically a Python function, or it's just a function basically that takes an input and outputs something. So there's also a good reason why batch learning is predominant. But with River, it's different because online models, they need to keep this ability to learn. So that's what you've been saying. So it's actually kind of straightforward, but the internal representation of most models in River is fluid, dynamic. It's usually stored in dictionaries that can increase and decrease in size. So imagine you have a new feature that arrives in your stream. Well, every model in River copes with that. They're not static. There's a new feature that appears, well, they handle it gracefully. So, for instance, a linear regression model is just going to add a new weight to its internal dictionary of weight. Now, in terms of serialization and pickling and whatnot, River is mostly written, well, basically, River stands on the shoulders of Python, very much so. So we do not depend very much on NumPy or Pandas or SciPy. We mostly depend on Python's standard library. We use dictionaries a lot, and that plays really nicely with the standard library. It's very easy you can take any River model, pickle it, and just save it. You can also just dump it to JSON or whatnot. Also, the paradigm of you train a model, you pickle it, and you have an artifact that you can upload anywhere. It's a bit different with online learning because you would play this differently. You would maintain your model in memory. So if you have a web server serving your model, you would not just load the model to make a prediction, you would just keep it in memory and make a prediction of it because it's in memory, so you don't have to load it anymore, preloaded. And then when a sample arrives, your model is in memory, and you can just make it learn from that. So yeah, I think the big difference is that you hold your model in memory rather than pickling it to the disk and loading it when necessary.
In terms of the use of the dictionary as that internal state representation, as you said, it gives you the flexibility to be able to evolve with the updates in data. But at the same time, you have this heterogeneous data structure that can be mutated as the system is in flight, and you don't necessarily have a strict schema being applied to it. And I'm just curious if you can talk to the trade-offs of being able to add that flexibility, but also lacking in some of the validation and schema and structure information that you might want in something that's dealing with these volumes of data.
So yeah, River uses dictionaries. So the advantages of dictionaries are plentyfold. First of all, a really important thing is that dictionaries are to lists what pandas data frames are to NumPy arrays. So a dictionary has names, and that's really important. So it means that each one of your features actually has a name to it. And I find that hugely important because, we always see features as just numbers, but they also have names, and that's just really important. Imagine you have a bunch of features coming in. Now, if that was a list or a NumPy array, you have no real way of knowing which column corresponds to each variable. If you switch two columns with each other, that could just be a really silent bug which would really affect you. Whereas if you name each feature, if the column order changes, well, the names of the columns are being permuted too, so you can kind of identify that. So what's really cool with dictionaries, and that works with River, is that the order of the features that you're receiving doesn't matter, because we access every feature by name and not by position. Dictionaries also are mutable in size. So, if a new feature arrives or a feature disappears between two different samples, that just works. So it's really cool also that dictionaries when you think about it, naturally sparse. So imagine that on the Netflix project, the features that you receive are the name of the user, semicolon 1, or the date 1, or you can just store sparse information in a dictionary. That's kind of really useful. There's this robustness principle that we follow with River. So the robustness principle is that is to be conservative in what you do, but liberal in what you accept. So River is very liberal in that it accepts heterogeneous data, as you said. So dictionaries that are different in size, dictionaries which have different orders or whatnot, but that is really flexible for users. So a common use case is to deploy River in a web app, and in a web app, you're receiving JSON data a lot of the time. So the fact that JSON data has a one-to-one relationship with Python dictionaries makes it really easy to integrate River into a web app. Whereas if you have a regular batch model, you have to mess about with casting the JSON data to a NumPy array. And that has a cost, actually. It actually has a cost because although NumPy, Torch, TensorFlow are, good at processing matrices, there's actually a cost that comes with taking native data, such as dictionaries, and casting them to a higher order data structure, such as a NumPy array. That has a real cost. In a web app where, you're reasoning in terms of milliseconds, well, you're spending a lot of your time just converting your JSON data to NumPy. Whereas with River, because it consumes dictionaries, well, the data you receive, I don't know if you're coding in Django, Flask, or FastAPI, the data you receive, your request, is a dictionary. So you don't have to convert the data. It just runs. So actually, if you take a River model, like a linear regression River and a linear regression in Torch, it's actually going to be much faster in River because there's no conversion cost. Plus, the features are names. And plus, you don't have to worry about the features being in mixed order or anything. So it just makes a lot of sense, really, dictionaries in that sense. Now, the pitfalls, obviously, it's not perfect. The pitfall is that I kind of disagree that there's a problem with the show of dictionaries. I actually think that dictionaries, well, if you wanted to, you could create, like if you're in Python, you can actually use a data class and you can convert that to a dictionary and feed that into your model. The data class helps you to create structure. So I don't think that's really a problem. Quite the contrary, I think. The fact is that also a dictionary can be nested. So maybe your features that you're feeding to the model doesn't have to be a flat dictionary. It can actually be nested. And that's really cool too. You could have features for your user, you could have features for your page, you could have features for the day, anything. Things that you cannot necessarily do with a flat structure, such as a data frame or an NumPy array. Anyway, I'm talking about benefits. I should be talking about cons. But yeah, I guess just the main con of processing dictionaries is that, if you wanted a River model to process 1 million samples, it would take much more time than processing 1 million samples with Pandas data frame or NumPy array. Because, the point of River is to be fast at processing one sample at a time, but not necessarily at processing 1 million samples at a time. But those are two different problems. So, although, you take Torch or scikit-learn, their goal is to be able to process offline data really quick. But the goal of River is to process online data, single samples, as fast as possible. And you're comparing apples and oranges if you want to do the comparison. It just doesn't work. So yeah, actually, you know what? I don't think there are real downsides to using dictionaries. It just helps a lot. And to confirm this, we have a lot of users who tell us about this. They say, well, it's actually fun to use River. It just makes sense because it's very close to the data structures that I use in Python. I don't have to introduce a new data structure to my system.
So for somebody who is using River to build a machine learning model, can you just talk through the overall process of going from idea through development to deployment?
I'm going to rehash what I said before, but I think the great benefit of online learning and River is that you can cut the R&D phase. So I've seen so many projects where there's an R&D phase and the model, gets validated at some point in time, but there's like a real big gap of time between the start of the R&D phase and the moment when the model is deployed. And the process of using River and any streaming model in general is to actually, as I said, deploy the model as soon as possible, monitor its predictions, and it's okay because sometimes that model, you can deploy it in production and those predictions do not necessarily have to be served to the user. So you just make the predictions, you monitor them, and it creates you a log again of training data and predictions and features. And that's what you call shadow deployment. You have a model which is deployed, is making predictions, but those predictions are not being used, to inform decisions or to change or to influence the behavior of users. They just exist for the sake of existing and for monitoring. One thing to mention is that once you've deployed this model, you have your log of events. That's the phase where you want to maybe design a new model. And you're going to have this model replace the existing model in production or coexist with it because you have a meta model or not. So I mentioned that you can take your log of events, replay it in the order in which it arrived, and have a good idea of how well your model would have performed. That's called progressive validation. So it's just this idea that if you have your log of events, every sample, you're first going to make a prediction, and then you're going to learn from it. So I have a good example. There's a dataset on Kaggle called the New York Taxis dataset, and it's basically a log of people asking for hailing a taxi for a ride, and they depart from a position, and they arrive at another position later in time. And so the goal of a machine learning system in this case could be to predict how long the taxi trip is going to last. So when the taxi departs, you want your model to make a prediction. How long is this taxi ride going to last? And so maybe that's going to inform, I don't know, the cost of the trip, or it's going to help decision makers, reorient the taxis, or I don't know, whatever. But you can imagine that this is a great feedback loop because you have your model making a prediction, and then later, maybe 18 minutes later or something, the ground truth arrives. So you know how long the taxi trip actually lasts, and that's your ground truth. And then you can compare your prediction with your model. And that enables progressive validation because you have a log of events. You have when the taxi trip departs, what was the value my model predicted, what features I used at prediction time, and later on I have the ground truth. And so I can just replay the logs of events for, 7 days and progressively evaluate my model. So I like this taxi example because it's easy to reason about and, taxis are easy to understand. But the taxi example is really what online learning is about. It's about this feedback loop between predicting and learning. And just to remind you, but how it would be with a batch model is that you would have your taxi dataset and, well, I don't know, you would split your dataset in two. You would have start of the week, end of the week, train your model on the start of the week, evaluate on the rest of the week. Oh no, the data I trained on for the start of the week is not representative of the weekend. Yeah, and it just becomes a bit weird. It becomes this situation where you're trying to reproduce conditions in real life, but you're never really sure of it. And you can only really know how well your batch model is going to do well in production. And online learning, it just kind of encourages you to go for it, to deploy your model straight away and not have to have this weird R&D phase where you live in a lab, you think you might be right, but then you're not really sure. And yeah, online learning just brings you closer to the reality, in my opinion.
As you have been developing this project and helping people understand and adopt it, what do you see as some of the conceptual challenges or complexities that people experience as they're starting to adapt their thinking to how to build a machine learning model in this online streaming format versus the batch-oriented workflow where they do have to think about the train test split, just the overall shift in the way that they think about iterating on and deploying and developing these models?
It's a hard question, but I think there's two aspects. There's the online learning aspect, and then there's the ML ops aspect. Now, in terms of ML ops, I think I covered enough, but it's much like a batch model. You have to deploy your model, which means maybe serve it behind a web app. As I mentioned, the ideal situation is to have your model loaded into memory, and that's making prediction and training. But all that is really harder to do than to say. The truth is that there's actually no framework out there which allows you to do this. You could do this yourself, and this is what we see. I mean, we get users who ask us questions in a River context or on GitHub or in mails, and they're asking us, how do I deploy my model? What should I be doing? And we always give the same answers. But the fact is that, we have these users who have basically embraced River and they understand it, but then they get into the production phase. And that's not what we're trying to, well, we feel bad because they are all making the same mistakes in some way. And River is not there to help them because that's not the purpose of River. So yeah, there's a lack of tooling to actually just, deploy an online model. So yeah, that's the ML ops aspect. I think in terms of sort of online learning, a big challenge is that not everyone has the luxury to have a PhD during which you can spend days and nights going through online learning papers and trying to understand it. And that's what I and others had a chance to do. But a lot of our users, they see the value of online learning and they want to put it into production, but they have deadlines to meet, right? They have to ship their project in 6 weeks and they just do not have the time to understand things in detail. So things like what I just described, progressive validation, it kind of takes them a bit of time to understand. And so again, what we need to do is to spend more time creating resources or, just diagrams to explain what online learning is about. And that in terms of library design, it's really important. Like if we wanted to introduce a new method to all our estimators, I would be against that. Like the whole point of River is to make it as simple as possible so that people can just, be productive, understand it. So yeah, I think that just to recapitulate, those are two problems, is that people do not necessarily have the resources to learn about online learning. And then there are operational problems around serving these models into production. So it's kind of like a batch model because you have to serve your model behind an API, and you have to monitor it. And these are things, that are common to a batch model, but there's the added complexity of having your model being, maintained in memory and keep learning and stuff, and things that are basically not common. I mean, if you had to Google it or find something on GitHub, you just kind of find these hacky projects, but no real good library to do that, at least not yet.
And one of the things that we didn't discuss yet is the types of machine learning use cases that River supports, where I'm speaking specifically to things logistic regressions and decision trees versus deep learning and neural networks. And I'm just wondering if you can talk to the types of machine learning approaches that River is designed to support and some of the reasoning that went into where you decided to put your focus.
River, again, is a general purpose library, so it covers quite a few things. There are some cases or flavors of machine learning which are especially interesting when you cast them in an online learning scenario. So if you're doing anomaly detection, so for instance, you have people doing transactions in a banking system, so they're making payments, and you might want to be doing anomaly detection to detect fraudulent payments. That is very much a situation where you have streaming data. And so in that case, you would like to be doing online anomaly detection. So we see that every time we put out a notebook or a new anomaly detection method, a lot of people start using it. We start having bug reports and whatnot. So it's kind of surprising, but it's a good thing. But yeah, I think there are modules and aspects of River which are clearly bring a lot of value to users. So that would be anomaly detection, but also we have forecasting models. So when you do online forecasting, that just makes sense. Like you have sensors which are, I don't know, measuring the temperature of something. People want to do that in real life, in real time. There's also a good example I have is we have this engineer who's working on water pipes in Italy. He's trying to predict how much water is going to flow through certain points in his pipeline. So he has sensors all over the pipeline and he's trying to just do a forecasting model. And so it just makes so much sense for him to be able to have his model run online inside the sensors or inside the IoT systems he's running. So just all that to say that there are some more exotic parts of River, such as anomaly detection and forecasting, which are probably bring more value than the classic modules such as, linear regression, classification, regression. Again, at the start of the show, I talked about Netflix recommendations. So we have some very basic bricks to be able to make recommendations. Well, we have factorization machines and we have some kind of ranking system so that if you have users and items interacting, you can kind of build a ranking of preferred items for a user. So we have these kind of exotic machine learning cases which provide value, but require us to spend a lot of time to work on them, basically. So it's very difficult for me and for other contributors to be specialized in anomaly detection, time series, forecasting, recommendation. But yeah, all this to say that River covers a wide spectrum. You can do pre-processing, you can extract features, you can do classification, regression, forecasting, anything. We try to, because it's online, it's just a bit unique.
In your experience of working with the River library and working with end users of the tool, what are some of the most interesting or innovative or unexpected ways that you've seen it used?
Well, unexpected is a good one. There's one thing that comes to mind. We have this person who is a beekeeper. So a person who is, taking care of bees, and I guess they, once a week or every 2 weeks, they go to the beehive and they pick up the honey in the beehive. And this person has many beehives, and so they don't like to waste their time going into the beehive and actually checking if there's honey or not. So they have a sensor. He has sensors that are in each beehive. They're kind of measuring how much honey is in each beehive, and he likes to forecast how much honey he is expected to have in the weeks or months to come, based on the weather, based on past data, based on I don't know what information he uses. But really, really just fun just to see this person doing this hackish project where they just thought it would be fun to use online learning to do it. And again, it was in an IoT context, so that made sense. I guess innovative, I was kind of impressed when I heard about this project of having a model within each car to determine where your destination would be. So I don't know, you wake up in the morning, you take your car, is it Saturday, you go to the market? Is it a weekday, you're going to work? It sounds silly, obviously, but having this idea of having one model per user is kind of fun. The most impactful project I heard about, and I know which is being used, is a situation where this company, they prevent cyber attacks. So they monitor this grid of servers and computers, and they're monitoring traffic between machines. And so they're trying to understand when some of the traffic is malicious and hackers basically trying to get into a system. So you can detect this by looking at the patterns of this traffic, right? And the trick is that behind the traffic, the malicious traffic, it's hackers, and they're constantly changing their patterns, so access patterns, to actually not be detected. And so if you manage to label traffic as, malicious, well, you want your model to keep learning. So they have this system where they have like thousands of machines, and they have a few machines that are dedicated to just learning from the traffic and in real time adapting, learning, detecting anomalous traffic, sending it to human beings so that they can actually verify themselves, label it, etc. And so it's really cool to know that Viva is being used in that context. Like, it just made so much sense for them to say, wow, we can actually do this online and we don't have to retrain. And batch learning was getting in their way. They had this system which was going at 1,000 miles an hour, just hundreds of thousands of data coming in all the time. And batch learning was just, it was just getting annoying for them. They having a system that enabled them to do all this online just made sense for them. And to know that you can do this at such a high amount of traffic, it was really cool and exciting.
In your own experience of building the project and using it for your own work, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
I think I'm just going to focus a bit on the human aspect here. But although I have been doing open source, for quite a bit, I've always had this approach where I probably work too much on new projects that I make myself rather than on existing projects. So I just rather just do things myself rather than contribute to existing stuff. And it's not always necessarily good, but it's just the way I work. And so River is really the first open source project where I work for other people. So like probably many people, a lot of my open source work is I just work on it myself. And obviously you work in companies and where you probably have a review process and you work with other people, but this is the first open source project where I really work with a team of people. And it's fun. It's just really so much fun. Like just a month ago, we actually got to meet all together and to have this like informal reunion. So that was really fun. And you realize that, after 3 years, there are ups and downs, and there's moments where you just do not want to work on River anymore, and you want to, you have work, you have friends, girlfriends, whatnot. And so the only way to subsist as a open source project in the long term is to have multiple people working. So doing open source, and it's not realistic to do it on your own if you want something to be successful and to actually have an impact in the long term. So it's actually really important to just be nice and to have people around you who help you. And although not everyone contributes as much as I do or core maintainers do, people help a lot and they make things alive. Like, it's always a joy when I open an issue on GitHub and I see that someone from the community has answered the question and I don't have to do anything. It helps tremendously. Yeah.
We've already talked a bit about some of the situations where online learning might not be the right choice, but for the case where somebody is going to use an online streaming machine learning approach, what are the cases where River is the wrong choice and maybe there's a different library or framework that would be better suited?
Well, yeah, again, honestly, I think that online learning is the wrong choice in 95% of cases. Like, you do not want to make the mistake to think that your problem is a online problem. You probably most of the time have a batch problem that you can solve with a batch library. Scikit-learn now, if you open it and you just run it, it's always going to work reasonably well. So sometimes I would just go for that. One thing we do get a lot is people asking how you can do deep learning with River. So they want to train deep learning models online. So the answer is that we do have a sister library that is called Torch River, and it's dedicated towards training torch models online. So, but again, that is a bit finicky at the moment and still needs some work being done on it. But yeah, if you want to be doing deep learning and you want to be working with images and sound and, structured data, River is not the right choice, even online. And you probably have to be looking at PyTorch.
As you continue to build and iterate on the River project, what are some of the things you have planned for the near to medium term, or any applications of this online learning approach that you're excited to dig into?
We have a public roadmap. So it's a Notion page with a list of stuff we're working on. That one mostly has a list of algorithms to implement. And it's mostly there to, make people know what we're working on and to encourage new contributors to work on something. So the few contributors we have just pick what they want to work on and, just in general order of preference. So for instance, me this summer, I've decided to work on online covariance matrix estimation. So if you actually an online covariance matrix is kind of useful because it's very useful in financial trading. And if you have an inverse covariance matrix that you can estimate online, that unlocks so many other algorithms, such as Bayesian linear regression, elliptic envelope method for anomaly detection, Gaussian processes, and whatnot. So I think I'm still in the nitty-gritty details of implementing algorithms and not necessarily applying them to stuff. I'm kind of counting on users to do the applications. It just feels right at the moment. Now, one thing I'm working on in the mid to long term is Beaver. So eventually I want to try to spend less time on River and work on a tool I'm building called Beaver. So Beaver is a tool to deploy and maintain online learning models. So essentially an MLOps tool for online learning. So it's in its infancy, but it's something that I've been thinking about a lot. So I recently gave a talk on it in Sweden. I've sketched a blog post and some slides where I try to describe what it's going to look like. But the goal of this project is to create a very simple, user-friendly tool to deploy a model. And I'm hoping that is going to encourage people to actually use River and to use online learning, because they're going to say, hey, okay, I can learn, but I can also just deploy the model, and and both tools play nicely together. So yeah, the future of River is to have Beaver and to have this reference tool to deploy online models. It's not going to be catered just towards River. The goal is to be able to, run it with any model that can learn online.
Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest barrier to adoption for machine learning today.
I'm always impressed by how much the field is maturing. I think that there's a clear separation now between regular machine learning, like business machine learning, I like to call it, and deep learning. I think those two fields are becoming like separate fields. So I've kind of stayed away from deep learning because it's just not my cup of tea, but still very interesting in business machine learning. So getting things done, I call it. And I think I'm impressed by how much the community has evolved in terms of knowledge. The average ML practitioner today is just so much more proficient than 5 years ago. And I think it's a big question of education and tooling. The tricky thing about an ML model when it's not deterministic, and so it's difficult to guarantee that its performance over time is going to be good, and let alone certify the model or convince stakeholders that they should adopt it. So in the real world, you don't just deploy a model and cross your fingers. So although we've gone past the test and R&D phase of a model, we are still not there in terms of deploying a model. And so the reality is that there's usually a feedback loop where you monitor your model and possibly retrain it, be it online or offline retraining. It doesn't matter. And so I don't think we're really good at that right now. I don't think that we have great tools to have human beings in the loop who work hand in hand with machine learning models. So I think that tools like Prodigy, which is a tool to have a user work hand in hand with an ML system by labeling data that the model is unsure about, they're crucial. They're game changers because they create real systems where you care about new data coming in, retraining your model, having a human validate predictions, stuff like that. So I think we have to move away from only having tools that are destined towards training a model, but we also need to get better at tools that, encourage you to monitor your model, to keep training it, to work with it, to, again, just treat machine learning as software engineering and not just as some research project.
All right. Well, thank you very much for taking the time today to join me and share the work that you've been doing on River and helping to introduce the overall concept of online machine learning. It's definitely a very interesting space, and it's great to have tools like River available to help people take advantage of this approach. So thank you for all of the time and effort that you and the other maintainers are putting into the project, and I hope you enjoy the rest of your day.
Oh, thank you. Thank you for having me. It was great.
Thank you for listening, and don't forget to check out our other shows, the Data Engineering Podcast, which covers the latest in modern data management, and Podcast.init, which covers the Python language, its community, and the innovative ways it is being used. You can visit the site at themachinelearningpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at themachinelearningpodcast.com with your story. To help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.